one very important concept is there that should be properly understood. You have hydrogen peroxide compound with which particular oxidation state of oxygen? Here in hydrogen peroxide, the oxidation state of oxygen is -1, right? Peroxides have oxygen in the form of -1 oxidation number, having oxygen in the form of -1 oxidation number. Now just recall the possible oxidation states of oxygen. In the elemental form, O2, oxygen has 0 oxidation number. In various compounds, the common oxidation number shown by oxygen is -2. Fine. Look at the two important changes. Water or any hydroxide formation will change the oxidation number of oxygen from -1 to -2, right? Also, if we convert hydrogen peroxide into oxygen, the oxidation number of oxygen in O2 is 0. So the thing is, hydrogen peroxide has oxygen in the oxidation state -1, which can be increased to 0 or that can be decreased to -2. The oxidation state of oxygen, that is -1, can be decreased to -2 or it can be increased to 0. So both the things are possible. So what can be concluded? Since both the changes are possible, that means hydrogen peroxide can behave both as an oxidizing agent as well as reducing agent. In all the reactions where hydrogen peroxide will act as an oxidizing agent, it itself will be reduced. It itself will be reduced from -1 to -2 oxidation state. So for this change, the reagent required should be of reducing nature, or in other words, I write here, for the reaction H2O2 acts as an oxidizing agent, right? H2O2 is acting as an oxidizing agent. It oxidizes the reducing agent, and the reducing agent is reducing hydrogen peroxide into water or some hydroxide compound. Come to this part. To convert oxygen from -1 state to 0, what do we need? The reaction with some oxidizing agent. If some oxidizing agent is reacting with H2O2, then the nature of H2O2 will be taken as a reducing agent. This is very important concept that we have hydrogen peroxide compound in both the roles. It can play the role of an oxidizing agent, it can play the role of a reducing agent. In the previous years, number of times the questions related to these two natures of hydrogen peroxide are asked. For all such questions, the basic thing should be very clear in your mind related to these two changes. Always keep in mind that if hydrogen peroxide is acting as a reducing agent, you will always get the product O2. If hydrogen peroxide is acting as oxidizing agent, it itself will be reduced into some hydroxide compound or in the form of water. So just remember the products obtained in the two cases, especially this one. Hydrogen peroxide, whenever acting as a reducing agent, should always liberate oxygen in that reaction. Now I am coming to the supporting reactions. Yeah, one more thing. One more thing usually come in our mind, that how do we decide in which particular case it will react, it will act as oxidizing agent or it will act as a reducing agent. So how to know about the reactions, how to know about the compounds? It's very simple. See, hydrogen peroxide has both the nature. It has oxidizing nature, it has reducing nature. But it will always depend on the reacting species, because the strong oxidizing agents will automatically make hydrogen peroxide to behave as reducing agent. If I have placed some reducing agent along with hydrogen peroxide, naturally that strong reducing agent will bring the hydrogen peroxide in the form of an oxidizing agent. For example, I take some reactions. Case 1, hydrogen peroxide as reducing agent. Let us take some of the reactions where hydrogen peroxide acts as reducing agent. One such reaction is the reaction between KMnO4 and hydrogen peroxide in acidic medium. The products of the reaction are reduced product MnSO4. Since manganese is changing from +7 oxidation number to the +2 oxidation number, oxygen will be liberated because hydrogen peroxide is undergoing oxidation. So this way KMnO4 with H2O2, they are giving the products oxidation product O2 and reduction product MnSO4. Now we can have some other examples. K2Cr2O7, again in presence of hydrogen peroxide with H2SO4, that is in acidic medium. Now please remember that in cold condition, actually here CrO5 is formed and it is not a redox reaction. Chromic peroxide compound is formed. But the slight heating of the reaction mixture results into a redox change. In the redox change, now chromium changes from +6 oxidation number to the +3 oxidation number. Here again oxygen gas is liberated. So the reduced product of K2Cr2O7 is chromium in the form of tripositive, and the oxidized product of hydrogen peroxide is oxygen. So we should keep in mind about the nature of hydrogen peroxide acting as reducing agent. I am talking about this part. So whenever hydrogen peroxide is taken as a reducing agent, it is liberating out oxygen. I take one more case, that is an important thing. Suppose we have ferric chloride and we have hydrogen peroxide. The required medium for this reaction is basic. As we have seen for the previous reactions, the medium required was acidic, and here in basic medium the reaction gives ferrous chloride, KCl, liberating oxygen. For balancing, H2O will also appear. So ferric is reduced in the form of ferrous. Hydrogen peroxide is oxidized in the form of O2. So these are some common reactions where we see hydrogen peroxide acting as reducing agent. We have one very interesting case, which is a common case also to be asked in the competitive exams, that is about reaction of hydrogen peroxide with ozone. Ozone. Whenever ozone reacts with hydrogen peroxide, the product of reaction is oxygen and water. Please be careful for the reaction, because in this reaction ozone is oxidizing hydrogen peroxide, or in other words I can say hydrogen peroxide is acting as a reducing agent for ozone. That's an important reaction. So these are some common cases where hydrogen peroxide is acting as a reducing agent. But let us once again recall what exactly was the nature of KMnO4. We know that in general hydrogen peroxide, in general KMnO4, K2Cr2O7, ozone are the common strong oxidizing agents. So if a strong oxidizing agent is there along with hydrogen peroxide, naturally hydrogen peroxide has to play the role of reducing agent. Now obviously when some strong reducing agent, say some sulfide, some iodide, this kind of species are there along with hydrogen peroxide, so naturally hydrogen peroxide will have a role of oxidizing agent for these species, iodide, sulfides, etc. So I am taking some supporting reactions, hydrogen peroxide as oxidizing agent. Let us talk about a few reactions where hydrogen peroxide is acting as oxidizing agent. Suppose we have Ki. Hydrogen peroxide oxidizes Ki into iodine. Look at the change. I negative is changing into I2. That means undergoing oxidation. At the cost of oxidation of iodide into iodine, hydrogen peroxide is undergoing reduction into hydroxide. Right? Another reaction where we find the similar nature is about the reaction with H2S. When H2S is passed in hydrogen peroxide, sulfur is formed in the reaction. So once again this is oxidation of sulfide into sulfur and the reduction of hydrogen peroxide into H2O. Hydrogen peroxide oxidizes metal sulfides into metal sulfates. Remember, PBS is a black colored insoluble substance. When H2O2 is reacted with PBS, the black PBS converts into white PbSO4. PbSO4 is a white colored compound. So this way the change of PBS from black to white is due to the oxidation process of PBS. The oxidizing agent taken here is hydrogen peroxide. I would like to add one more case. In a comparative manner it will be important for us. This is about some ferrous compound. Hydrogen peroxide when reacts with ferrous compound in acidic medium, the ferrous compound is oxidized into ferric and hydrogen peroxide is reduced in the form of H2O. So we have these common reactions related to hydrogen peroxide where it is acting as oxidizing agent. Now I come to one more important thing related to hydrogen peroxide. You just compare this reaction of H2O2 and this reaction of H2O2. Are you able to find some interesting comparison in the two? Let us see. In that reaction, hydrogen peroxide was acting as reducing agent for ferric. In this reaction, hydrogen peroxide is acting as oxidizing agent for ferrous. Right? So here I show the conclusion. Ferrous can be oxidized into ferric by the use of hydrogen peroxide, but the required medium will be acidic. Here let us compare the conversion of ferric into ferrous by the same reagent hydrogen peroxide, but the required medium is basic. That's an important comparison, the important conversions. Actually, these two changes are possible because ferrous and ferric +2 and +3 oxidation numbers of iron are stable. So, since both the oxidation numbers in case of iron compounds are stable for iron, then a ferrous compound can always have a possibility to be oxidized. And when ferrous undergoes oxidation, hydrogen peroxide is acting as oxidizing agent, or in other words we can say it will be reducing hydrogen peroxide. When ferrous undergoing oxidation, it can reduce hydrogen peroxide. When ferric is taken, once again, ferric has a possibility to go in the form of ferrous. So it itself can be reduced. When ferric reduces into ferrous, the role of hydrogen peroxide will be as a reducing agent. Or in other words, hydrogen peroxide itself will undergo oxidation in this change from ferric to ferrous. So that way the iron compound can be converted from ferrous to ferric or from ferric to ferrous depending on the medium taken for the reaction. Here are few reactions supporting the nature of hydrogen peroxide as oxidizing and the reducing agent. Now finally in the topic, I tell you about volume strength related to hydrogen peroxide. Although the topic is connected to the concentration terms that usually come into the solutions, whenever we talk about the mixtures, solutions, we usually follow the concentration terms like molarity, molality, normality, mole fractions, etc. But here in case of hydrogen peroxide solution, we follow the concept of volume strength. It's a small thing, just try to understand it. As we know, hydrogen peroxide decomposes giving H2O and oxygen, right? This is a simple decomposition reaction of hydrogen peroxide. The decomposition reaction of hydrogen peroxide. Nothing more than that has been shown here. Now I am talking about a term called as volume strength of H2O2 solution. Volume strength of H2O2 solution. Let us recall some common things related to gases, some common things related to concentrations and number of moles, etc. Can we read this reaction in terms of the balanced form, the number of moles, the stoichiometry of the equation? Let us read it. 2 moles of hydrogen peroxide decompose to give 2 moles of water and 1 mole of oxygen. Okay, I repeat, 2 moles of hydrogen peroxide decompose to give 2 moles of water and 1 mole of oxygen. Now let us talk the things in some other manner. Can I say the solutions of different types of hydrogen peroxide? If I take various types of hydrogen peroxide solution, then can we use the language like this? A solution that contains 2 mole of hydrogen peroxide will liberate 1 mole of oxygen on decomposition? Yes, we can use. I repeat, what is the language? I am using the language, a solution containing 2 moles of hydrogen peroxide, the rest will be water, right? A solution containing 2 moles of hydrogen peroxide will liberate 1 mole of oxygen on decomposition. Is it correct? Now, tell me, related to gases, what do we say in terms of Avogadro's law? Although Avogadro's law is related to the volume of gases and their number of particles, the formal language of the law is equal volume of all the gases when kept at the same temperature and pressure contains the equal number of particles. Now here let us talk about the standard condition of temperature and pressure. In the standard condition of temperature and pressure, temperature 273 Kelvin, pressure 1 atmosphere. In the standard condition of temperature and pressure, what is the volume occupied by 1 mole of any gas? 22.4 liter. In the standard condition of temperature and pressure, the volume occupied by 1 mole of any gas is 22.4 liter. Right? Now, I am combining these statements and just reading this equation once again. Just try to focus on the statement, on the language. A solution which contains 2 moles of hydrogen peroxide will liberate 22.4 liter oxygen at STP on decomposition. Is it the correct statement? Yes. I repeat. A solution that contains 2 moles of hydrogen peroxide will liberate 22.4 liter oxygen if collected in the standard condition of temperature and pressure in the decomposition reaction. Right? I write this particular statement now. In the decomposition of hydrogen peroxide, if the solution contains one mole of hydrogen peroxide, then it liberates what do you say? What should I write? 22.4 liter? No, because now in the language I have taken 1 mole of hydrogen peroxide. The matter was initially taken in this form. For 1 mole of hydrogen peroxide, the product obtained is, initially we were saying 2 moles of hydrogen peroxide give 1 mole of oxygen, or we were saying 2 moles of hydrogen peroxide give 22.4 liter oxygen. So naturally, if I am talking about 1 mole of hydrogen peroxide, then how much of oxygen gas will be liberated at STP? Half of that volume, that is 11.2 liter. So the decomposition of hydrogen peroxide, if the solution contains 1 mole of H2O2, then it liberates 11.2 liter oxygen gas at STP. In this way, any solution which has X moles of hydrogen peroxide, you can come to the number of moles of H2O2 by any of the concentration terms, like molarity, molality, or whatever, normality, mole fraction, etc. But if you come to the conclusion that hydrogen peroxide present in that solution is 1 mole, then you can say the volume strength of that solution is 11.2 liter. Yes, this is called as the volume strength. I use the language for this. Therefore, the volume strength of H2O2 solution containing its 1 mole quantity is 11.2 liter. The volume strength of H2O2 solution containing its 1 mole is 11.2 liter. Of course, this is expressed at STP. So now we can say that volume strength of H2O2 can be determined by using the formula 11.2 into number of moles of hydrogen peroxide. Now the number of moles of hydrogen peroxide can be obtained either through molarity or through molality or through that mole fraction. We can use any kind of concentration terms. As an example, molarity into volume gives number of moles, right? Molarity into volume gives number of moles. So if the concentration of hydrogen peroxide has been given in the form of molarity, if we know the volume of that solution also, then multiplying molarity by volume, we get the number of moles of H2O2. If we know the number of moles of H2O2, then multiplying that value by 11.2 gives us the volume strength. So it is simple. Before coming to the volume strength, I mean the conclusion related to the volume strength, you should properly know about the number of moles of H2O2 present in that solution. So you can easily relate the volume strength. Now, questions can be asked in vice versa manner also. The volume strength of particular H2O2 solution will be given. Its volume can be given. Molarity is to be determined. That can be a question. So volume strength, if this is given, this is a constant value. Number of moles of H2O2 can be written as molarity of H2O2 solution into its volume. So molarity can be determined if we know the volume and the volume strength, right? Volume and volume strength. If these two things are known, then the molarity can be determined. So one of the three things are usually asked: molarity, volume, volume strength. So if we know the other two terms, we can determine the third one. This is all about hydrogen peroxide, its preparation, its properties, the determination of its volume strength, and the structure of hydrogen peroxide, peroxide linkage. Remember, all these points are very important and they are repeatedly used in the various topics in chemistry. So along with this part, the entire topic hydrogen and its compounds, that is over. Thank you.